Hey guys, so today there's the round 701, Division 2, and hopefully this is the actual starting time because it was delayed by 15 minutes just as I started my previous recording, so that's fun. Because there's no school today, I can actually do a screencast for once, and also the same thing for the edu round because there's no school on Monday, so that's awesome. Just give a thumbs up, but you couldn't see it, of course. And yeah, so we're gonna do the standard things, updating the sub count, stuff like that, and etc. And also, if you haven't heard, I'm finally coming back with another topic stream after like multiple months by this point. So you can vote on the topic and just see general details here by clicking on this tab and then, just doing whatever. Currently DP is winning. If you don't want that to happen, you gotta vote. So yeah, and this contest is the plan. So hopefully things work out. Let's go. Apparently there's also some background noise going on right now. I'm not sure if you can hear that, but that's gonna be distracting eventually. Alright, let's do this. You have two positive integers, a and b. You can perform two kinds of operations, divide a by b and increase b. And floor division, you want a to be 0. Okay, so I think I've seen some sort of similar problem before. Actually, I didn't get my writing tablet, so I should do that. I think I've seen some similar sort of problem before. The idea is division is more effective the bigger the denominator is. So if you're going to increase b, like say you do something like this where you increase b and then divide by b and then increase b again. But like, why would you do that instead of just doing all the increases first? Because if you do this before the division, then the division is going to be strictly more effective and you're going to do the same moves anyway. So you want to do all the increases before you do the divisions because the division will only be more effective. And so my guess is that there's no reason to increase b past like a certain point, past like square root a or something. Because like past that point, it's sort of more effective to divide because the division will be very fast in that case. So I think it's enough to just like try increasing b up to square root. Which is like 100,000 or something. And then because wait. So if b plus I is greater than 1, because if it's 1, there's no point in doing that. And that way also, because we're doing division, we'll have at most log n or log a divisions, so all these steps should be rather quick, I think. Yeah. So while x is greater than 0, so we increment the number of turns and then do a division. X divided by b plus I. Should be fast enough. I think we can cut it down to something like that if necessary. I don't have multi-tests. Do the compilation. Yep. 4, 9, 2, 12, 3, 1. Okay, perfect. And just to make sure it's greater than 1, do the divisions, turn, divide, blah, 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 blah. Right, and so I is just, in this case, it's just the amount we're going to increase b by. That's just what I'm using to represent that. Okay. Given a positive integer to k, two arrays are called k similar if they are Oh, 62 milliseconds. Okay, we're good. Two arrays are called k-similar if they are strictly increasing. They have the same length. All their elements are positive integers between 1 and k, and they differ in exactly one position. Although I'm not exactly sure what the bound is for how much you would want to increase on A, but like, I think it's like around log actually. Because you can do it in log n division, so more than log moves is stupid. But, you know, whatever. Just huge number really doesn't matter. Like, I can make this 50 or something, it would still pass. Given a positive integer k, two arrays are called k-similar if they are strictly increasing. They have the same length. All their elements are positive integers between 1 and k. And they differ in exactly one position. Okay. You're given an integer k, strictly increasing array A and Q queries. For each query, you're given two integers Li and Ri. Your task is to find how many array B exists such that B is k similar to that. Okay. Alright, that's sort of fun. So, how would this work? So say you have some array like, say you have some array like this. How this works? So it's like, oh, what? So you have like 2, 4, 7, and 9, and say k equals like 9 or something. Okay, right, so we're querying this array, and we're going to say that we want an array that's k similar to this subarray, right? Yeah, find out how many arrays B exist. So it must differ in exactly one position. So here's how this works. This element can be between 1 to 3. Because we can imagine sticking a 0 on here and then sticking like a k plus 1 on the end of this, and that way it sort of makes it easier. So this element can be between 1 and 3 because like it's sort of like just it has to be strictly increasing, but it can also differ. And if we're going to make this element differ, then it can be between 3 to 6. And if we're going to make this element differ, then it can be between 5 to 8. No, 5 to 9. Okay, so is there anything going on here? 1 to 3. So we have some overlap, kind of. That's the basic idea. So I guess we can just figure out the range of every element. Something like... It's kind of annoying. Is there a nice way to do this, or is it going to be not nice? I guess it's going to be not nice. We got 11 here. Okay. I guess that's just how it's going to be. Yeah, so... Basically, if we consider some range, only the endpoints really matter. Everything else, all these other elements are going to be whatever their range was in the original array. So like, the fact that we have this subarray doesn't change the fact that this element can be between 3 and 6. The only ones that matter are the ones on the end, because now they have sort of a 0 and a k plus 1 on the end. So I guess the strategy is we can do some sort of prefix sums or something, and I don't know, this feels kind of overcomplicated. That's the thing. Two, 4, 6, and 7. And there's not much else I can do, is there? Like 1, 9. Yeah, okay. So we can basically figure out how much. So basically every element can like become any other element from its range. So it can become like, for example, this can become 3 other elements and it can form 3 of those arrays. So then we sort of have some numbers that we're interested in like keeping the sum over. And I guess the way to do that is with prefix sums or something. And then we subtract out the endpoints and then handle them manually, I guess. I don't know. I don't have a better way. So that's what I got. So we're gonna do some prefix sums. Bi if. Oh, wait. Okay. First of all, I'll do that. Okay, so if I is greater than 0, of equals ai minus 1. If I is less than m minus 1, just taking the left and right values, then, okay. So the number of elements, let's say we have A, B, and C in strictly increasing order. So we can get any element on the range a plus 1, c minus 1, which has c minus a minus 1 elements, and then we subtract 1 because we can't have b, so we have c minus a minus 2 elements in between. So bi equals rv minus lv minus 2, r plus equals bi, ci equals r. So using c for prefix sums. Then so if there's one element, then we can print anything, basically. That's how it works, right? Yeah. Okay, so cout. Here we can change to any element except the original one, so we can have k minus 1. Otherwise, we do the prefix sum stuff. Okay, right? So what we're going to do is CR. If L is greater than 0, S minus equals CL minus 1. This is sort of basic prefix sums, and then we exclude the endpoints. So RV is equal to AL plus 1. S plus equals and actually we can just do this straight up where we exclude, we take the prefix sum but we exclude the 2 endpoints of the range, and that should work. Yeah, so we just increment L by 1 and decrement R by 1, and that sort of makes the prefix sum represent this range. Okay. Just being slow today. RV minus LV minus 2. LV equals AR minus 1. RV equals K plus 1. That's the basic idea. We're just manually correcting the endpoints. I feel like there's something more elegant, but I don't know. So perhaps not. We do not have multitests anymore. Okay. 8789769 43. Okay. Looks good. Handle the endpoints correctly. Do the prefix sums. Yep. Alright, that was fun. That took a long time. I don't know what's up with that. Okay. Well. Alright, we're a bit slow. Let's go faster. A pair of positive integers a, b is called special if the floor division of a and b is equal to a mod b. Here, a divided by b is the result of the integer division between a and b, while a mod b is its remainder. Okay? You're given two integers x and y. Find the number of special pairs a and b such that a is between 1 and x and b is between 1 and y. Alright. Seems like it would have something to do with square root because t is small and that's usually how it works with these problems. But who knows? So let's find out. The floor division of a and b is equal to a mod b. Alright, so what does that entail? So if we represent, if we do the like Euclidean thing where we represent some number x, so like we have a and b. So if we represent, if we take integers k and like r, and then we represent a as kb plus r, where like it's sort of the Euclidean, I don't know what it's called exactly. It's like the Euclidean division thing or something. But this is the idea that you can represent any number in the form like this, where k and r are integers also. And then so let's call back to a class I'm taking right now. So r is going to be a mod b. A mod b. And k is going to be floor of a over b. Somehow these have to be equal. So if k is equal to r, then we have like a is equal to r of b, r times b plus 1. And then therefore a over b plus 1 is equal to r. Actually, it might be easier to represent this as k. And then a over b plus 1 is equal to k, which is equal to the floor of a over b. Now, does that help? And actually, does that even work? That's the first question. So we want k and r to be equal. I mean, that's sort of like if k and r are equal, then that's true, but is it the other way around too? I guess it isn't necessarily equivalence relation. So 3 and 2. Okay, definitely not. Wait. Well, it's true for the samples. That doesn't necessarily mean anything. So what else would it mean? I feel my brain deactivating somehow. This is not going to be a good day. Just to icing on the cake. We're recording, right? That'd be good. Yeah. So A must be between 1 and X, and B must be between 1 and Y. Right. How do we count such integers? Okay, first thing, something we can notice is that, close that before that gets, something we can notice is that A must be greater than B, or greater than, greater than B, because otherwise, like say A is less than B, then A mod B is equal to A, but floor A over B is equal to 0, and because A must be greater than 0, that's not possible. So we need, and if A is equal to B, whoa, that's some handwriting right there. If A is equal to B, then like A mod B is equal to 0, 0. But the floor of A over B is equal to 1, so that doesn't work either. So we need A to be greater than or equal to B. Does that help somehow? If A is greater than or equal to B, then I guess we can do some like math. So let's fix some C equals like square root of 10 to the 9th or something. So if B is less than or equal to C, then A mod B is less than C. And if B is greater than C, then like the floor of A over B is less than like 10 to the 9th over C or something, right? So I guess there's some sort of idea there that we get small and large numbers kind of. Oh, what's going on? So if B is less than or equal to C, we get some stuff going on. So how can we solve for small b then? If we have I feel like fix a specific value of A mod B. Like say A mod B is equal to X. Then floor of A over B is also equal to X. So then I guess we can apply the same equation now. That A is equal to A over B, A times B plus A mod B. It's equal to xb plus x, which is equal to x times b plus 1. So I guess for a given b, it's like not that big. How would that work? So, okay, I guess that sort of confirms my equation that it sort of goes both ways, I guess. Because if A mod B is going to be equal to X, then you have to have this form. So basically we're interested in the number of multiples of b plus 1 we can get. Which is to say we want the value of a, the floor of a over b plus 1. Or rather, if we use these bounds, then it's the floor of x over b plus 1, where x is the upper bound given in the input. So we want the sum of that, I guess. And then are we using the trick to like count the number of stuff that happens? Okay, this is not well solved. So I'm assuming this is correct because otherwise it would be something really easy. I'm gonna assume we're using the trick to count the number of like, we want the sum from I equals 2 to what is it, y plus 1 of the floor of x over I. I think the easiest thing to do is binary search, because actually wait, say we want a over b to be x. Then that means that x is the greatest integer such that bx is less than or equal to a, which means also that the floor of a over x is equal to b. So b is the greatest integer where a over where bx is less than or equal to a. So then if we increase x, we get a different floor value. Or if we increase b, we get a different floor value. I know there's a formula to figure out exactly how this works, but I'm not remembering it, so let's just do binary search since it's the easiest way. Okay, cn to x to y, and we bring test cases back. So floor is equal to x over it. LV is equal to x, no, it plus 1, RV equals y plus 2. We're basically binary searching on the last value where the floor value is the same. Because the basic idea here, which I haven't even said, is that there are only like, there are around O of square root y, or square root x, I guess, distinct values of the sum. Because if I is less than or equal to square root x, then like there are only that many values. There are only square root x values where this occurs. And if I is greater than square root x, then x over I is less than or equal to square root x or something like that. Or O of square root x, meaning that there are only square root x possibilities here and square root x possibilities for the floor division there. So this should finish quickly. It should be like root n log n or something. Or root x log x or something. And y doesn't really matter that much. Okay, so if x over m is equal to f, then go to the right. Else L equals, no wait, go to the right, so set the L value. Else we need to go deeper, so go to the left. Jesus. M. Okay, now ants plus equals f times r minus it exclusive, then it equals r. See if that works. Okay, cool. See out ants. Where am I getting stuck? I'm getting stuck on the first one. What's happening? How am I not reading in the values here? Wait, am I doing binary search wrong? Oh, whoops, yes I am. Okay. Alright, that's dumb. Don't do that, kids. That's not good. And adults. That's just a saying. I'm not trying to be condescending. Alright, now we get Jesus, come on. Now we get a different value, so that's a problem. How will we get a floating point exception? What are we dividing by? LV plus RV over 2. Oh, because I didn't. Okay. Did it again. I don't know why I don't use L and R, because that's easier, and that's clearly what I'm used to, so maybe it's smart to be consistent with your variable names. Oh, come on. Oh, yeah, right. Same mistake 3 different times, obviously. So let's see. That's wrong, that's wrong, that's wrong, that's wrong, that's very wrong. All of them are wrong. Awesome. What's with that? What is with that, indeed? Am I just wrong in how this works? Wait, let's just look at this. Perhaps I've done my math wrong, who knows? So we get a lot of values. A lot of values, yep. How do we get that? So we get 0, answer 0, 1, 2, and 4. Two and 4. What? So it can't be 1. Oh, maybe we start from 3. Because I guess, yeah, the B can't be 1. Because that wouldn't work. 1 is a special case. Does that fix things? I would assume it doesn't. I don't know why it would, actually. Fixes things somewhat, but not that much. Actually, so we get 1, 0, 2. Then we get 28, which is fun. So 50 to 3. What else am I missing? Oh god, right. Oh my god. Oh, this is annoying. Right. Because we can't go above the value itself. Okay, so the floor value is going to be small enough to ants plus equals min. So we can't go above the floor value itself, and we can't have it be 0. So the possibilities are it minus 1, and then x over it. So this is sort of a special case with the small values. Or is it it minus 2? How does that work? I'll check the values and see if they work out. Okay, yeah, so that's how that works. Try that just as a special case. 5, 3, 3, 8, 4. Okay, yeah, because if the values are small, that's sort of annoying. Because we can't have repeats, so we can't have what would it be, 17, 3, because the pairing 7, 3, no, 8, 3 will work because floor 8 over 3 is equal to 2, and 8 mod 3 is 2. But if we do the same thing, if we fix 17 mod 3 is equal to 2, but the floor value is bigger than 3, so that doesn't work. We can't have repeats, so we have to cap it out at the value itself. And so we do it minus 2 because it is equal to b plus 1, and we can get any value on the range from 1 to b, which is b minus 1. Is that right? 1 to 2, yeah. So it's b minus 1 possibilities, and then extra minus 1 because it is b plus 1. So that's why we cap it out there. Let's make sure this works again. Should work within time. It's not that slow. That's messy. God. Okay. And I'm just slow today. I don't know what's happening. Okay, that gives us that. You're going to matrix A consisting of positive integers as n rows and m columns. God, I'm not liking these problems. You're going to matrix A consisting of positive integers, n rows, m columns. Construct a matrix B consisting of positive integers. It can have the same size, and Bij is a multiple. K to the 4th? What? And the absolute value of the difference between numbers in any adjacent pair of cells is equal to k to the 4th for some integer k greater than or equal to 1. What the hell? What the hell? What is this? K to the 4th. Alright, what's so special about k to the 4th then? I'm guessing 4 is arbitrary, and then it could be really any power. But 16 is sort of a thing. 16 to the 4th is something interesting. Is it always possible? Yeah, it's always possible. Okay. So we can have so we don't have that many differences, actually. We can have, geez, there's a lot of notes for a C. But as always, it comes down to messing with the equation. So k to the 4th. So k and then k to the 4th. So we can have 1, 2, we can have a lot actually, but k to the 4th, the powers of 4 go 1 and then 16 and then 81 and then 256 and then what's the 5? It's 3125 or something. No, 625, is that what it is? 5 to the 4th. Okay, yeah, and then it continues. But the idea is these numbers grow very quickly, so there aren't that many numbers that we could possibly have. And it has to be a multiple of aij. So how is that something we could do? Okay, the fourth. Why is this significant? I guess the idea is that these values aren't that big. 10 to the 6 is also sort of a small bound. Is that too big? It's definitely too big. Yeah, okay. So that's not gonna work. Screw that. Thinking about GCDs and stuff like that, it's not gonna work. Seven, 11, and 2. So we need to be like 7 to the 4th, and then 11 to the 4th, or 22 to the 4th. It'll be 14 and 11. Well, it doesn't have to be the LCM, does it? So what I've been currently thinking about is if we have some numbers like this. So if we have some previous x and then we're trying to figure out some number y that corresponds with it. If we take the GCD of x and y, is that even necessary? Sure, wait, we just need to fit y to whatever x is. No, okay, I don't know if this goes anywhere. I don't even know if it does. Does it? What are the differences that we get? So we have like 15 and then 65, then 175. I know that like if we do these differences out, then we're gonna get some patterns going on. Like we have 50, 110, and then it continues. That's not really the interesting part, is it? Oh, it's all x and y. Okay, I see the statements now. Um, like, what would we do for two numbers even? So we get that bx minus ay is equal to k to the fourth for some k. What is up with the fourth? Does that have any significance, or is it just a filler? It's just an arbitrary number they can use. Can make it 1 if we so desire. Actually, using like some theorem like Bézout's theorem or something, I don't know how to pronounce it, but we can like get any number that's a multiple of GCD of A and B for their difference. So we can take GCD of A and B to the fourth and do that, because the numbers are up to 16, so that's possible. But that only works for a pair of integers. It doesn't work for the grid, I would guess. Another thing that's interesting is that the numbers are up to 16, meaning that like maybe it's possible to just map every number to a new number so that like no matter what happens, the like we map 1 to like A1 or something, and then 2 to A2, and then 3 to A3, regardless of what the matrix even looks like, and then 4 to A4 and so on. And then we make it so the differences are always a power of 4 between everything. Is that something we could do? It's like regardless of what the matrix even is, because theoretically we could have it so they could have a matrix where everything's like that. Like they could test all possible adjacencies. Actually, even that depends, because you could have equal values, so that's annoying. That's not fun. Okay. So you could have equal values, so that doesn't even work. But still you have a small possible amount of numbers. It's not a good contest to be tired for. Actually, it's never good to be tired for a contest, but who knows? Have the numbers be increasing, it doesn't matter that much. What's 583 minus 408? Is that relevant? 175. Yep. Okay. Another idea. What's the LCM of 1 to 16? Let's do some code to crunch some numbers. Multitests. 720, 720. Okay, that's smaller than 10 to the 6th. That's interesting. That's interesting. Maybe that's useful. I had an idea and then I forgot what I was going to do, but I can remember that idea, so let's go for that. So you can make like all of the numbers the same. If we raise them all to 720, 720, then we need to like decrease or increase some of them, I guess. Now, how do we do that? Well, we can't make it LCM to the 4th. That's not possible. But we could do some sort of a grid. That's sort of a possible idea. Like if we have a checkerboard pattern, let x equals 720, 720, which is again just the LCM of 1 dot 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 to 16. Then if we have x and then like in like a checkerboard in like a checkerboard pattern, chessboard, doesn't really matter, right? So then we do something like this. Then like all of these numbers are all of these numbers are totally unrelated to each other. Right, so we can just make these whatever we want. So let's make blue equal to x plus ai to the 4th. And that does it. That's it. Yeah, we're done. Okay, cool. So, because then the difference will be ai to the 4th no matter what. So for c into x, if I plus j mod 2 is equal to 0, x equals 720, 720, else x equals 720, 720 plus x times x times x times x. I don't even need the matrix actually. cout. Cool. Okay, that was nice actually. That was cool. Yeah, I like that. So yep. 16 to the 4th looks good. And this. Yeah, alright, cool. Alright, so that does that. Not doing the best. Sort of slow in the way this goes, but what the hell? He has A. What is second thread doing? He has A, B, D, and F. Okay. So does F have more solves? Alright, I guess this is something we want to do then. You're given an array of integers b1, b2, bn. An array is hybrid if either it's equal or it's a prefix sum. Okay. Cool. Maybe that's something to go for. Okay, we get a tree. All right, let's look at this for a bit. So an array is hybrid if for each I at least one of these conditions is true. Find the number of hybrid arrays. So either we add the value or we double the prefix sum. That's something of note. Either we add the value or we double the prefix sum. So because we double the prefix sum, if the prefix sum is 0, that's a thing. Otherwise it's not. What does that mean? Does it mean we can do a weird DP? I don't know. Is that how that works? I guess like either so either we set bi to ai, or we it's not sorry, it's not that we double the prefix sum, I guess. It's that we make the prefix sum that. So we make the prefix sum that. fix like the previous time that we fixed the prefix sum, then let's see. All right, so let's take some array. Six array, like, I don't know, what are the values? I don't want to use specific values because it's sort of weird. A3, A4. Or rather, no, we have the B values that are fixed. B1, B2, B3, B4, B5. Alright, so let's say we fix the prefix sum at B3. If we never fix the prefix sum at all, then that's fine. If we last fixed the prefix sum at B3, and now we're at B5, then we know we took B4 as is. And then the prefix sum at B3 is going to be exactly, or like, this prefix sum is going to be exactly B3. And then we know that we took the array elements in all of this range. So we get two new arrays if this is different. We get two new arrays if this is sort of like, if the element required to fix the prefix sum is the same as the array element, then you get one new array, otherwise you get two. That's the idea. So we can do an n-squared dp, or we can notice that all of the transitions are the same, except we subtract out the number of ways that we need to get yeah. We subtract out the number of ways that we need to get that. All right, I need my mod-op template. Alright, so we say let this prefix sum be, so this prefix sum is B3. We know that. And so we have B5 here. So we're going to make this prefix sum equal to B5. Let's see. It's a bit of formula bashing, I guess. So we want the number of values, like f of I, or rather, we want to subtract out all f of j, where like bi is equal to bj. Wait, how would this work? We want the prefix sum itself to not be equal to the value. this work? Is it that the prefix sum can't be 0? Is 0 the magic value here? I guess it must be 0, right? Yeah. If it's 0, there's nothing we can do. Otherwise, we, like say it's 1. And if the prefix sum is... okay. So I'm interested in the number of ways where the prefix sum is not 0. So it's basically saying, bi plus bi plus, or wait, no, bj plus bi plus 1, no, j plus 1, dot 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 I minus 1 is not equal to 0. So I guess that would work for something. Why are there multi-tests here? Let's try something. V equals 0. Whoa. I equals 0, I is less than I plus plus. So V equals 0. Right. Remember ways to have that be different, I guess. How does this work? So it's like ants minus count, what was it? R. Right, then if let's see. If this prefix sum is not 0, then I don't know, this is an idea. I'm not sure if it's entirely right, and I just want to see like how crazy it is. I've just been thinking about the details of the way this would work. Could be wrong. Doesn't even handle a multi-test. Wait, what? Why is it not? What is it doing? Did I not do the compilation right? What is it doing? What have I done to my own code? N3. Oh wait. I'm not reading in the values. Okay. I guess that does it. Yeah. Hang on, let me submit this first and then explain it afterwards. Sweet. Alright. That's pretty good. So people have AK'd now. Alright, second thread is crushing us on speed, but we're not doing that bad. We're not doing that bad. We had a pretty slow beginning, but this is pretty good. So now we gotta solve E, and that's it. So the basic idea is that we want to count the number of... So basically, like, okay, let dp of I... We're going to count the number of arrays that are different from taking bi equals ai the whole time. So let dp of I be the number of... Actually, you know what? Wait, I'll solve E and then I'll... You know, there's no point doing commentary after I've solved it. I'll just like, I'll go over this in the solutions. So don't worry about it. I will remember this. Yeah. Well, why? I don't know why I would. Okay. Let's just read E, figure out how to do this. You're given n-1 integers and a tree with n vertices rooted at vertex 1. The leaves are all at the same distance d from the root. That's cool. And recall that a tree, yeah, the distance between two vertices is the number of edges. If two vertices, yeah, definitions. Initially, there's a red coin, a blue coin on the vertex 1. Let R be the vertex where the red coin is, and B will be the vertex where the blue coin is. You should make D moves. So you can move the red coin to a child. Move the red coin to a child. Move the blue coin to any vertex B. Move the blue coin to any vertex B that's on a lower level. I see. You can optionally swap the two coins. Whoa. Okay. Interesting. Cool. All right. So you can move the red. You have to move the red coin to a child. You can move the blue coin to any possible value, and then potentially swap them. Now, what's the idea with swapping? Alright, so we gotta figure out the way this works. How are people doing? Alright, so people are... Whoa. Shovel 1 in my room. Nice. Okay, this is not that bad. We're doing pretty well. Move and swap. Move and swap, move and swap, move and swap. Come on. Note that R and B can be equal at any time and there's no number written on the root. Oh, you gain the difference between them. Okay. The difference between the positions of the two coins. So because of the way this tree works, because all the leaves have to be at distance d, every new level has at least as many vertices as the previous level. So that's something interesting. Meaning that well, what would it mean? What if we do like DP on the position of the first coin or something, or the red coin? Because it doesn't matter where the blue coin is, does it? No, it doesn't. It doesn't matter where the blue coin is, because next move it can go anywhere. Is that it? Is that all we need to do? No, it's not. Yeah, the thing is, it doesn't matter where the blue coin is, because next move it can go anywhere, right? So, really we're just interested in where the red coin is. So is that actually it? Well, actually the problem would be transitions. But because every level has like not that many things, no, that's not gonna work. We want either linear transitions or not that many transitions. So let's figure out how we do a transition. So the current idea is dp of I and A. So on the ith level, why am I using my mouse? On the ith level, too used to this. And then I don't know why I'm using blue either. But dp on the ith level and red coin at A. And the sum of the number of states is O(n). We just need to do transitions quickly enough. And how do we do that? So if we have the red coin at some point, yeah, it doesn't matter where we move the blue coin. So the sum of the transitions might be O(n) too. Say we don't swap. If we don't swap, then the red coin goes to a child, and then the blue coin goes wherever it wants to minimize the value. So we just want the closest value in the level. So that's easy. So if we don't swap, then red goes to a child. And again, because we don't care where the blue is, we just take the blue to the closest value. Now, if we do swap, then it's a bit messier, I suppose, where we have some stuff going on. So the blue will go to a child. And the red will go anywhere. So what we want is the closest child, I suppose. So how would this work? It's sort of a complicated transition. So like the closest child, right? So what we need to do is swap the conditions. We need to fix the place red's going to and find the best previous value for that. How do we do that? That's a good question. One that I don't know how to answer. Okay, that's kind of annoying. Alright, so what we're going to do here is we're going to fix anywhere. So let x equals anywhere. Now iterate over x in increasing order. And then like the cost of the children. Okay, we're going to sort of maintain the sets of the costs of children. So like basically we have this previous layer. And then we have this new layer. What the hell? And we're fixing some value here. We're fixing some value, for example, here. And we're interested in the minimum value over all children of, or over all layers, over all the previous layers of DPI plus closest value to red, to x, where this is x. Now the key is if we iterate x in increasing order, then the closest value only changes O of orange times in total. And so we can maintain like the set of the costs for each child and then do the DP that way. I think that works. And that should work, yes. Okay. All right, so let's implement it now. This should be fun. More people are solving this, that's fine. Okay, so we have multitests. Why the hell do we have multitests? Why do we multitest on like everything except for B and D? Okay. Like D could totally have multitests. It's not even that like, I don't know what they're doing. Alright, so C into N for I equals 0, I plus plus, edges I dot clear. Let's just get that out of the way. 200,005. This is gonna be weird to implement. Okay, but that's fine. We can handle it. We'll be good. At is gonna be the nodes at each depth. Okay, so. Okay, now, let's do some DFSs. Oh, wait. Oh, this could be easier than I thought then. Okay, so C into X, edge between vertices I and VI. Okay, so edges I dot push back minus x. Actually, this should be child. We don't even need edges, actually. That's cool. DFS 0. and then depth 0. Now for depth v equals d. Okay, now for, at v dot push at d dot push back v. Now for li equals 0, also maintain the max depth. Theoretically, we don't need to do the DFS for this, but whatever, because of the way the input works, but it's fine. I is less than max d, I plus plus. Alright, let me do a little dp. Let's not mix those up. Do we need the depths actually? Whatever. dpi is equal to 1e17, dp0 equals 0. Now dpi is going to be the answer if the red chip is at I. Okay. Because again, it does not matter where the blue chip is. Alright, so so first we're going to do the first type of transition where we don't swap. Then red will go to a child. So for LO J at I, at the depth I. And then for each child, we get simply, if we go from J to K, then dp k equals min dp k, or of dp j plus closest. Right. dpj. I'll make it. Okay, why not? So then auto it is equal to, so wait, for LO J at I plus 1 vowels, then insert AJ. Just put all of them into a set. Vowels dot lower bound AK. If IT is not equal to vowels dot end, if IT is not equal to vowels dot begin, then search the previous element 2, and then look for that. Okay, then dpk equals to min dpk, dpj plus close. Cool. And now we have the other transition, which is more messy. Oh, we want the maximum. Oh, okay. Max. Wait, max? Oh, shoot, okay. We want the farthest values. Okay, wait, I just like misread this. So we want the farthest values. Wait, that makes this a lot easier then. Okay, so min equals min AJ max equals max, max AJ. Man, this would have been cooler if it was smallest, I think, because it would be harder and we would have to do some messy set stuff, but I guess not. Alright, that's dumb. Okay, so this should still be 0. So for LOJ at I, for LOK at child J. So far is equal to max abs AK minus min, or rather it's not even abs, AJ minus min, max minus AJ. No, AK. Okay, and then how does this work? Let me see how these transitions change. MB equals min, MB AK, and XV equals max, XV AK. Okay, so mn equals min, mn mb minus dpj, and max equals max. I'll get into how this all works later. dpj plus xv. LOJ at I plus 1. dpj is equal to the maximum of the previous dpj, and then we can go up or we can go down. So max minus aj, aj minus min. At max d minus 1. Pretty sure I solved the harder problem. It's kind of unfortunate. I don't need that anymore. But I should do some stuff. Child I dot clear at I dot clear. And then depth will be reset. What? I don't need any of these. I don't need any of these. Okay. Yeah. And then dp will be reset every time. Yeah. J and I plus 1. Let's see if this works. Does not work. Okay. So how far do I get? Oh, okay. Whoa. What? What's max D? How? How are you that? How are you that? Oh, that's a cool diagram. Okay. How are you this though? how did this happen? Max t equals 0. What? Oh, it's not necessarily children. Okay. Fine. I don't know why they would do it that way, but... I thought they were cool, and then it turns out they aren't. That's sad. If x is not equal to p, okay, child x, child v dot push back x. 0, -1, 0, right? So child v dot push back x. Man, okay. That strictly increases my chance of bugs, but we'll see how this goes. Still dies. Some issue that we can figure out. Okay, so something is just up. Alright, so dp values are all 0. How's that even possible? Is this just randomized, I guess? What the hell is happening? 0 is the root. Alright. So we're doing this right. We are not doing this right. X is not equal to p, dfs xv d plus 1. How is this happening? Edge is I dot push back x. So it means we have an edge between I and vi. Right? How is this happening? What is happening? Oh god, okay. So just get stuck somehow. I don't know what's with that. I'm so confused. Oh wait. Okay. I'm confused, yeah. I'm just so lost. Okay, there we go. So there's something finally happening. Alright, we're doing the ats right? Oh, wait. Let's see. Let's just see if we're doing this right. So we have 0, 1, 2, 3, 4, 5, 6, 7. Okay, cool. So we can get rid of that. $14, $45, $163, $123. Okay, let's just make sure everything's good. So we're clearing everything, I hope. We have DP being reset every time. Now we read in the edges, do it correctly. A0 equals 0, read in the values. Okay. Now for all of these, DPI equals 0. Do the min and max, take the farthest values, not the closest. Again, it would be a lot harder if we were interested in taking minimum. So maybe I can leave that as a challenge to you or something. Yeah, looks good. Do some magic voodoo math. Okay. Alright. We've AK'd this div 2. Nice. That's pretty good. Alright, so give me 1 second. I'm gonna get water and then I'll go over all of these solutions and everything. Be right back. Alright, give me a few more seconds to finish this up. Just mute my mic for this. Alright, we're back. So let's check once again if anything's happened. Oh, my rank went down. That's sad. Well, we're good. So yeah. Props to second thread for doing well. After being screwed so many times out of things, it definitely deserved a good performance. So yeah. In terms of my own performance, I was really slow on the earlier problems. That was not good. That sort of sucked. But then I woke up. Basically, that's what happened. I woke up and then everything worked out. So D was cool. E was interesting. Could have been harder. F was nice. The rest of them were sort of like more standard, but I guess that's how it is sometimes. I don't know the smooth way to do B. Maybe there's a better way to do it, but whatever. So without further ado, let's just go over these solutions to everything, and we will leave it at that. So I'll go through A to F in order, and also I'll have a challenge for A in case you're interested. Because I misread a problem. I misread E, I misread E, solved the harder version, and then only realized it like right after I solved it. So that's frustrating, but what can you do? Just read the problem better. Alright, A is rather simple enough. So you have two numbers, A and B. You can do two operations with it. One, you can set A equal to the floor of A over B, where the floor is defined to be the greatest integer x such that x times b is less than or equal to a. Or you can increment b. I'm not going to use the colon equals because I'm lazy. So you can increment b. So let's consider some sequence of operations where we possibly increment and then do a floor, and then increment and then do a floor, and then increment, or etc. First of all, there's no reason to divide when b is less than 2. So assume we only divide when b is greater than or equal to 2. And therefore every time we divide, we decrease the values by a certain amount. Every time we divide, we at least have a, meaning that it's going to get small very quickly. So another thing to note is that consider this operation. It makes b larger, and the larger we make b, the more effective this division is going to be, because like that's just how it works. I assume we have a large number. It may be better to just do that because potentially like making b larger could make the division more effective and make it so you have to do fewer divides, right? But if we do a division and then we increment later, then the division we do is going to be weaker before the increment than after the increment. So if we instead swap these operations to make it so the increment is before, then the division is just going to be stronger because b is larger. This is like a primitive form of exchange argument. So what we're basically saying is that we want to do all the increments before we do any of the divisions, because an increment will make the division stronger. So that's how we do the operations. So basically, once we figure out how many increments we do, then we just need to like divide a by b until we get to 0. So we figure out the number of increments we do, and then we simulate the division until we're done. Now the key point is that also that because the floor of a over b is at least halved each time, like the number of operations we do is going to be really small. Like it's going to be log base 2 of a, which is like 30 or so. So if the number of increments we do is much more than 30, then there's no point in doing that many increments, because like even in the most basic, like if we increment by 1, then we'll have b being greater than or equal to 2. And then just with that, we can be done in 30 operations. So if we increment like a lot more times, like if we increment 100 times, then no matter what, we're going to be worse than this initial strategy we have. So there's no reason to increment more than like O of 30 times, right? So basically, we only need to try a small number of values for possible increments. If we try something like 100, then it will work in O of t times 100 times log something time, which is like 100 squared times like 30 or something, which is 3e5, and totally, absolutely fine. And this is a very weak upper bound too. It could be stronger. But the point is, we only have to try a small number of increments. And in fact, my solution goes up to like much bigger, like 100,000 or something, or 30,000, yeah. So that's the idea. Do all increments before we divide, and then try brute force the number of increments, and then just like simulate the process. And we don't need that many increments, at most like 100. So we can just try all of those possible values. Okay, that's A. For B, I don't know what the point of B was. I guess maybe there's a cool way to do it, but it just felt like implementation for me. So I don't know. So 2, 4, 6, 7, 8, 9, we have an array. We are given a bunch of queries. In each query, we're asked some range of the array. It's not a good one. We're asked some range of the array. And what we're interested in is we want to create a new array where A, the values are between 1 and k. Or let's say we want to create a new array B where the values are between 1 and k. What are the conditions? They're strictly increasing. So every next value has to be strictly greater than the previous. They have the same length, so it's just like another array of the same length. And they differ in exactly one position. So that means that every element is the same except for one of these, which could be different. Okay, so imagine we just did the naive brute force, right? Let's brute force the element that's different. Yeah, we brute force the element that's different. So say this element is going to be different. Well, it has to be between 4 and 7. And it has to not be 6. So the number of, not less than or equal to. It has to be between strictly 4 and 7. So 4 and 7 gives us this range 5 to 6. And we already know that 6 is on this range because the initial array is also strictly increasing. So 6 had to be between 4 and 7 in the first place. Meaning that we have this range and then we automatically lose 1 from this range. So the size of this range is going to be 7 minus 4 minus 1. Because like if we have that A must be less than X, which must be less than B, then we have the range A plus 1, B minus 1, which has length B minus 1 minus A plus 1 plus 1, because it's inclusive. So which simplifies to just B minus A minus 1. And then we get an additional minus 1 because we have to exclude the current element that we have, because we can't have 6. So ultimately we end up with B minus A minus 2. So that's the answer for an element. It's the difference between the two adjacent elements minus 2. The only special case is when we're at the ends, because the end, there's no element on the left. So what we can do is, it must be between 1 and k. Which is equivalent to saying it must be strictly greater than 0 and strictly less than k plus 1. So what we can really do is just like stick on imaginary 0 and imaginary k plus 1 to the end here. And then now we're solving for that. So the ends are kind of special. But everything else, like if both of its adjacent elements are already in the array, then like that's it. If both of its adjacent elements are already in the array, then whatever our subarray is, the answer isn't going to change. I mean that if we like create an array of answers, and also these endpoints are special as well. So if we create an array of answers, like let's say we had 2, 4, 6, 7, 8, 9. We stick on the virtual elements 0 and k plus 1. In this case, k equals 9, so we have 10. Then the answers are, so this is 4 minus 0 minus 2, so this can be two things, which corresponds to 1 and 3. This can be two things, this can be one thing, this can be no things, this can't change at all, and this can't change at all. Or wait, yes, this can't change at all. So if we query some range, like say we query this range, these two elements are unaffected because both of their adjacent elements are in the array. And any element that isn't the two endpoints will be unaffected. Only the two endpoints are special. And if L is equal to R, if the range is size 1, then the answer, it's a special case. The answer is just k minus 1. Because it can be any value except for itself. Yeah. So that's the idea, I guess. Possibly there's some sort of telescoping stuff here where you can like cancel a bunch of stuff out and it turns out to be some function of the length of the array and the endpoints or something. Maybe that's possible. Maybe you can do some sort of math like that. But what I did was I just created a prefix sum array over this green array. And then you can use the prefix sum array to query the range that's unaffected. So now all you really care about is manually computing the endpoints, and you can literally just compute the answer for these. Like once again, you stick a virtual 0 on the end of this and a virtual k plus 1 on the end of this. And then you figure out the answer for this one, and then you figure out the answer for this one and add those to the total. And that's how you resolve a query. You use the prefix sums to get the bulk of it, and then you correct the endpoints manually. And this is sort of similar to a USCO problem that I did actually, so that's kind of cool. Or one that I didn't do but I thought about, right? So here you have the special case, if L is R, print k minus 1. Otherwise, do the prefix sum, and then just find the answers for the endpoints, and then figure that out. And this is computing the prefix summary. Okay, so for C, I was not a fan of this. I think it's cool up until the point where you get to the point where the constraints are 10 to the 9th, and then it's like not cool. And actually, it's mathy no matter where you go. So basically, you have integers x and y. You want to pick integers a and b. So you want to find the number of pairs a and b, where a is between 1 and x, b is between 1 and y, and some more stuff is going on. We must have that the floor division of a over b is equal to a mod b. Now the key is that like we can represent any number as in terms of b, some number k and some number r, where like a is equal to b times k plus r, and r is between 0 and b. This is like well known. It's like Euclidean division algorithm or something. I think that's what it's called. But basically, it's like how division works. It's some multiple of b plus a remainder. So sorry, it's some multiple of b plus a remainder, and that's just how division works normally. So notice that in this form, r is equal to a mod b. That's just what a remainder is. And k, therefore, must be equal to the floor division of a and b, because because it's everything that's not the remainder. So you sort of round R down to the nearest multiple of B and then do that. And that's what you're doing with floor also. It's sort of a similar operation. So for this to work, we need K equals R. So let's fix some value of R now. Let's say R is equal to A mod B is equal to X. So then, I forgot how I did this actually, but how did this work? Wait, there was some derivation I had of this that I sort of forgot. It would be nice to have back up again. I've been talking into a mic, right? I hope so. Hang on, let me figure out how this derivation works. So if we fix R, I guess it works that way, yeah. Then A over B is also equal to R. So if we represent the values in this form, then A is equal to B times R, because K equals R, plus R. So A is equal to R times B plus 1. And therefore A over B plus 1 is equal to R. Right? Yeah. So, now we want to figure out for which R is this satisfied. So now say we fix some B. So we basically want the number of R that this works for. So for example, say we want B equals something and then R equals 1. Then A has to be B plus 1, exactly. Say we want R equals 2, then A has to be 2 of B plus 1. And we can do this for every R between 1 and B. Note that also that B has to be greater than 1 here, otherwise this doesn't work. There's no possible answer for B equals 1. So we also assume B is B is strictly greater than 1. So R is between 1 and B. And yeah, this is the idea. So we can figure out how many R's are possible. And the way to do that is to just find, well, either we can get every R that's possible. Actually, no, sorry. R has to be strictly less than B. So either we can get every R that's possible. And so what we get is, we can get every R between 1 and B, which is B minus 1 possible values. Or like the required value of A is too large, or the required value of A exceeds X. So there's some value C where like A is equal to C times B plus 1, but that's greater than X, which is too large. So we want to figure out what's our limit. What's the largest possible C that we can get without exceeding X? And this is asking the largest C such that C times B plus 1 is less than or equal to X. And this is the definition of the floor division. Yeah, this is the definition of floor division. The largest integer C such that c times some values less than or equal to x. So the best c we can get is the floor of x over b plus 1. So for some b between 2 and y, the answer we get for this b is x over b plus 1. And that's it. Now, if I were setting this problem, I would have left it here because there's not much else that is interesting. It's just like an extra part to the implementation. Oh, and also it's like, sorry, it's not just that. It's the minimum of b minus 1 and that. Because also we can't have more remainders than like are possible. So, yeah, this is the like I don't know why they had to make it 10 to the 9th. That just makes implementation a lot more annoying. But now the basic idea is, this is a well-known thing, that the number of distinct values of the floor is like O of root x or something. Because consider this. Say b plus 1 is less than or equal to is less than or equal to root x. Then automatically there are only like root x possibilities for this, because there are only root x values that are less than root x. So otherwise we assume that b plus 1 is greater than root x. But then, but then the floor of x over b plus 1 is, because as we increase b plus 1, the division gets smaller, it's less than or equal to the floor of x over root x. So the value of the floor division is less than or equal to root x. So in this case also we only get root x possible distinct values for the floor. Meaning that if we iterate over the explicit floor value, then we're done. And so it's kind of hard to iterate over the explicit floor value. So what we can do instead is we can group together particular values of b that have the same floor value. So say we had some range c and d, where like x over c plus 1 is equal to x over d plus 1, then all of the values on this range are going to have the same answer. So what we can do is something like binary searching for the largest value of b that still gives you the same floor value, and then you can compute all of these values at once. And we also have to explicitly handle this case because we have this other minimum constraint. But the good thing is, when we get to this point where b minus 1 is greater than root x, then the floor value is automatically going to become the minimum, because this is like less than root x, and this is by definition greater than root x because b is greater than root x. So after we get to a certain point large enough, we can ignore this other condition. But for the small values of b, we have to consider both of this. So what I did was I just naively iterated b from like 2 to like 10 to the 5th or something, because that will by far exceed root x, whatever root x would be. And then you just literally compute this value. And then for b greater than 10 to the 5th, you do this sort of binary search. So you figure out whatever the current floor value is, and then let this be c. And then binary search on the largest d where this is still true, where the floor values are all going to be the same. And then you can compute the floor value and then add like the size of the range, which is like d minus c plus 1 times x over c plus 1 or something. And then that's your contribution to the answer for that. And then you move on to d plus 1 and you continue until you get to y. And this takes at most O of root x time because this brute force is simple. And then the other iterations, because they're only root x distinct floor values, this binary search happens at most root x times. So you get O of something like root x log x, and y is kind of irrelevant. Or it's more like root x log x plus root y or something. I really don't see why this is necessary. Because getting to this, in my opinion, is like the interesting part. After this is just like standard stuff. So I don't know. That's speculation. Let the problem setters do their thing, and I will do my thing and solve them. And we'll leave it at that. But yeah, that was kind of annoying. So at this point, this is where I started liking the contest, when I solved this one. Because this, like, the previous problems were not that great, but at the same time, they're not for me, so I don't have the best right to judge them. But this is where it started getting cool. So here you have a matrix. You have a matrix like something like 1, 2, 2, 3, right? And every value is between 1 and 16. So that should stand out to you immediately. 16 is tiny. Why would they possibly do that? Why would they make the constraint 16 when they have the size of the matrix 500? And the size of the values can be up to 10 to the 6. That's huge. What do they need 16 for? Why is it so small? We'll get back to that later. But for now, let's finish reading this statement. You want to create a new matrix where every new element, create a new matrix of the same size, where every new element is a multiple of the previous element. So for example, this can be like 20 because it's a multiple of 1. This can be 18 because it's a multiple of 2, but it can't be 17 because that's not. So this can be 18, this can be something like 6, and then this has to be a multiple of 3, so this can be like 9 or something. Totally random numbers, right? Yeah. So then what we're going to do is we're going to look at all the differences between adjacent elements. So like, for example, this, and then this, and then this, and then this. Elements that are next to each other in the matrix, either vertically or horizontally. Now, the absolute differences between these elements, like so for example, this absolute difference is 2, this is 14, this is 3, and this is 9. All of these absolute differences have to be powers of 4. That's the interesting part. So like, what? Right? Powers of 4? Values up to 16? What could this even mean? So like at a certain point, you sort of get the idea that 4 is a bit arbitrary. It could be like any value as long as it's small enough. Like we could have made this squared or cubed and it would have been the same problem basically. So in some cases, in some rare cases, 4 is special. And there's some special property about the power of 4 that matters. But if there's nothing that seems to be standing out, then try just ignoring the 4 and focusing on the rest of it. Because 4 is so arbitrary that it's like, it just feels like it shouldn't matter that much. It's just an extra constraint that just happened to be difficult enough to include in the problem. And in fact, it turns out that 4 is the smallest number because everything else would force it to exceed 10 to the 6th. But like, just let's ignore the 4 for now. Maybe it'll be useful later. Maybe we'll need to come back to it. But for now, let's sort of get rid of it. Throw it out. Because like, how much would the problem change if this was k cubed instead of k to the 4th, or k squared instead of k to the 4th? Alright, so now we're going to scope out some solutions to this. And of course, this matrix doesn't work because none of the differences are powers of 4. And also, it can't be 0, so we can't make everything the same. But say we could do something like that. Say we were able to make it so also all the new values have to be positive. They can't be 0. But say some values could be 0, like 0, 0, 0, 0. Say some values could be 0, but the differences couldn't be 0. So what we can do is, when we sort of have these adjacent differences problem, a good thing to think about is a chessboard. Because say we color all the vertices like, how does this work? Say we color all the vertices red or blue. And then we do something to the reds, and then we do something else to the blues. Right? Now, every adjacent difference is going to be between a red and a blue. So if we can engineer the reds and the blues in such a way that, like, the blues are totally irrelevant to each other and the reds are totally irrelevant to each other. No red is adjacent to a red, no blue is adjacent to a blue. So we want to engineer the reds and blues in a way that every red satisfies the property with every blue and every blue satisfies the property with every red. Now the question is, how do we do that? Is there some sort of way to handle reds and blues differently? Now, if we can make some value 0, then it turns out we can. Let's just choose all red values to be 0. So we have 0 and then 0. And then we had some initial values like A in row 1 in column 2, and then A in row 2 in column 1. Now we want these differences to be powers of 4, and the easiest way to do that is just to make these things powers of 4, because everything else is 0. And so we make it just aij to the 4th. Wait, aij to the 4th, and this becomes that too. And now every difference is between 0 and a power of 4, meaning that it's going to be a power of 4. So that's great. The only problem is that we can't have zeros. But this is where the constraint of 16 comes in. This is why it's important. We don't have to decrease each value. What we really want, we don't really need zeros. What we need is some value x where no matter what the initial value of AI, no matter what the initial array value is, we can still raise that value to x by it being a multiple. So we need x to be a multiple of all the initial values of 1, 2, 3, 4, etc. And we also need x to be less than or equal to 10 to the 6th. Is there such an x? And the answer is yes. This is the least common multiple from 1 to 16, which is a well-known thing. And as it turns out, you can figure this out via computation, Wolfram Alpha, writing code for it, whatever. It may help to use that the LCM of A and B is equal to A times B divided by the greatest common divisor. There's some intuitive way to understand that, but I'm not going to explain that here because this is just computation. And it turns out that we can take x equal to 720, 720. 720, 720 is divisible by all of these numbers simultaneously. So, yeah, that's cool, because that just means we're done. Right? Like, that's all it is. Instead of making these 0, we can generate this matrix and then just add 720, 720 to all of these. Now this works because, again, 720, 720 is a multiple of every number, meaning that we can add this and not have a problem. And this matrix initially worked, and because we're looking for absolute differences, if we add something to everything, it doesn't change any of the absolute differences. So adding this works. So really that's what our matrix is. We're going to, in all of the these diagonals, in the first partition of the chessboard, like the black squares or the white squares, however you want to think about it, we're going to have just x. And then the remaining values in the gaps, we're going to have x plus aij to the 4th in every value. And then it's clear to see that every adjacent difference is now a power of 4. Can't draw. So the final question is, does this fit? And indeed it does, because the maximum value is 16, 720, 720 plus 16 to the 4th is only 780,000. So this fits within the constraints. And therefore we're good. Okay, let's check my submissions. Did we FST anything? Oh, wow. We got everything. So system tests are crazy fast. Indeed, we can see that we are closing in on the AK. Second thread crushed us. Yeah, that's fun. So that's cool. It's just slightly ahead the whole time. Interesting. Yeah, so that's the idea. Seems like a lot of people didn't end up AKing this round. Okay, so wait for F to test, but I don't have doubts. It had multi-tests, so I think it's good. Alright, E is cool also. Although I ended up misreading it, and I solved the harder problem than what it initially was. So that took up a lot of time, and other than that, yeah, I'll leave that problem as a challenge. Basically, the challenge is, this asks for maximum, but what if you wanted to solve for minimum instead? It's sort of the same idea, it's just like, it's just sort of different. Yeah, so we're solving for, the challenge is to solve for the minimum number of points instead of the maximum. It's actually just like a more annoying version, and the main idea doesn't change, but you know, whatever. That's what I thought it was, because the other problems were annoying too. Like C had annoying constraints. So, alright, here's the idea though. You're given a tree, and the special property of this tree is that, let's say for example like this, it's not necessarily binary. Like I can have something like this. Actually, let's take the input tree. Let's use the sample, because why not? So, you're given a tree. Actually, wait, let me draw this a bit more nicely. We're caring about depths here. How does this work? And then here. And then 2 here. 1 here. 1 here and 2 here. Cool. So yeah, the idea with this is to, each thing has a value as well, except for the root, because the root doesn't matter. So we'll draw values on all of these. 2, 3, 7, 7, 6, 9, 5. And 9, 7, 3, 6, 6, 5. Ah, why did I make the tree red? Okay, that was dumb. But, okay. Can I flood fill this, or is it gonna... Let's try this. Oh god. Alright, that worked pretty... Actually, it wasn't that bad. Sure, I'll take it. So, you have a red chip and a blue chip as well. So you have a red chip and a blue chip. I'm not going to draw circles. Let's just say you have a red chip and a blue chip. In every move, you can... in every move, you're going to move the red chip and the blue chip down the tree. So the red chip can only move to a direct child of the current vertex. Meaning that if a red chip is, for example, here, then it can only move here because this is the only child. If it's here, then it can move to here and here, but it cannot move here because this is not a child. And the blue chip can move anywhere on the next depth, regardless of if it's a child or not. So if the blue chip is here, it can move to any vertex on the lower depth. Notice that at every point, so you're moving the red chips and blue chips like simultaneously. Notice that at every point you're going to, the red and blue chips are always going to be on the same depth. And then the third thing you can do is, say you move the red chip down and you move the blue chip down, then if you want, you can swap them. So the red chip takes the place of the blue chip and the blue chip takes the place of the red chip. Then the score you get is the absolute difference between the values of the tree. So for example, this absolute difference would be 7 minus 2. And say I had, like, say I just moved these down here, and then I move this down to here. Then this absolute difference gained would be 7 minus 5, and this would be 9 minus 6. And the score is the sum of the scores you get for each individual thing. And you want to maximize your current score. Again, my challenge for you is to solve it where you have to minimize. But here you have to maximize. So that's the idea. Now, how do we do this? Well, again, notice that the red chip and the blue chips are always at the same depth. So say we define some sort of dynamic programming where we have dp on the depth, so say we're currently here, and then the position of the red chip and then the position of the blue chip. So we say we're at this depth, the red is here, and the blue is here, for example. Then the transition from one depth to a new depth is to try all the possibilities. We can move red to any child, we can move blue to any other position, and we can possibly swap them. And then this is how we do updates. The problem is this is like n. With naive transitions, it's like n to the 4th or something. No, n cubed. Because the red has a total of n possible positions. The blue has always n possible positions, and there are n squared possible previous states for each depth. And there could be a lot of depths. So it could be like, I don't know what this complexity is, like n to the 4th or something, maybe? Some huge number, n to the huge. So we don't want that because n is 10 to 2e5, so that's really bad. Let's make an observation. First, notice that we can move the blue chip to any position on the next depth, right? That's the definition of the problem. So if we've already accounted for the cost of, or the score that we get from these values, and wherever the blue chip is, we don't care where the blue chip is anymore. Because no matter where it is on this level, it can move anywhere. It doesn't matter where the blue chip is. So we can cross this off. We can get rid of the blue chip from our state. So now we have a dp on the position of the red chip, or on the depth and the position of the red chip. So automatically this is O of n states, because like for each depth, like the sum of the number of positions of the red chips over all depths is n. It's just the number of nodes. So really you can also think of it like dp of v, where it's like the best answer if the red chip is at b. And then that's another way to think about it. It's equivalent. I did it that way in my own code, but you can do it however you want. I think dp of like with the depth and the actually we can call this dp of r. Yeah. Just the position of the red chip. I think having depth explicitly as a parameter is sort of easier to explain. But I would not recommend actually coding like that. It's easier to just use it. So say we're going to transition from some depth to some other depth now. The problem is that, again, the red chip can go to any child, meaning that the sum of the number of possibilities for the red chip is only like the number of nodes in the new layer. But the blue chip can go anywhere. So it's like the number of nodes in the new layer squared. So that's not good. Because that's n squared possibly. But let's break our transition into two possibilities, because we can solve these possibilities independently and then combine their answers at the end or something to form the DP. So first, we assume we don't swap. Then what happens? So red just simply moves to a child, and blue can go anywhere. Note that once again, we don't care where the blue goes. We just want to maximize the cost function. So we can iterate over the child the red one goes to, because again, there are a total of O of n children, so that's fine if we do that. We can iterate over the child. And then we just need to find the best position for the blue chip. And the best position for the blue chip is the one that maximizes the absolute difference. And like, say we have a bunch of points on a 1D space. And then the absolute difference is the difference between the points, or the distance between the points, right? So like, if we pick some point and we want to find the answer for it, obviously like, the only things we care about are the two endpoints, because anything else, anything in between is going to be closer to this current point than the two endpoints. So really all we care about are the two endpoints. And the two endpoints are simply the largest value on the depth and the smallest value on the depth, which we can pre-compute. So really we only have two possibilities instead of anywhere. Blue can go to largest, the largest value, or the smallest value. And then say we go from vertex J to vertex K. I'm sorry for my handwriting, by the way. Then we update dp of K to be the minimum of, or the maximum dp of K, and dp of J plus the maximum of the largest minus AJ and the smallest minus AJ, or AJ minus smallest, or like the absolute difference, whatever, it doesn't really matter. And this isn't weird notation, this is just like me saving lines. All right, so dpk, a particular value is maximized with itself and its parent plus the best position for the blue. So we're moving the red from J to K. So initially we get dpj because that was our previous value. And then the additional amount we get from this layer is, actually, sorry, this should be a sub K. The additional amount we get from this layer is just the best place we can move the blue vertex to, which is either the largest or the smallest. So we try both and we take the maximum. So that's it. There are only oven total children over the whole tree, so this transition in total is oven. And the other part is if we do swap. Now, if we were solving for a minimum, this would be a lot messier, but we aren't, so this is easier. So then we can think of it like this. Red can go anywhere because it's going to be swapped with blue, so it sort of takes the role of blue. And now the blue vertex has to go to a child, or the blue chip has to go to a child. Now, if we iterate over anywhere, then we possibly get an n-squared transition, so that's not good. If we iterate over anywhere and then like iterate over the children, then that doesn't work. But let's instead do it sort of in reverse. We're going to fix the place that red goes to. We're going to say that red's going to go here, and then over all of these, we're going to find the best position. We're going to find the best previous position. So let's fix the point X where red is going to go to. Or let's call it K again for consistency. So we could come from anywhere. So for example, we can inherit the dp value from any of these. And what we're interested in is the largest child. That's how this works, right? Yeah. What we're interested in is, like, for example, say we go here. Then say we're going to come from this vertex. Then what we get is, let this vertex be x. So we get dp of x, because that's just what the answer is for this, plus the blue vertex, the red vertex will go here. And the blue vertex will move into some child. We don't care which child, we just want the one that maximizes the answer. So which child are we going to? Well, once again, it's the same argument. We want either the largest value in the child or the smallest value in the child. So it's dpx plus the maximum of go to largest or go to smallest. Let's consider these cases independently. So first we're going to solve for largest and then we're going to solve for smallest. So dpx plus largest minus ak minus a sub k, or dpx plus a sub k minus smallest. So we want to find the x that maximizes this. So let's let Lx be the largest for x, just like some notation, and Sx be the smallest for x. Whoa. So then this becomes Lx, and this becomes Sx. So now we have like values. So for a given k, we want to find the x that maximizes this. Notice that we've already gotten rid of the absolute value conditions. So now what we want to do is we want to isolate x. So from here, we can mess with this equation a bit. So we get dp of x plus Lx minus a sub k. Notice that this only depends on k, which for the purposes of choosing an optimal x is constant, and this only depends on x. But this x is sort of universal over all possible choices of k, because at any point we could come from any x to get to any k. So if we pre-compute for all x the largest value of this, then we're done. So yeah, that's it. For all nodes of the previous layer, we're simply going to pre-compute this value. And then the answer is just the maximum of ak plus the pre-computed best over all x. And then we're going to do the same thing for the other one. Notice that if we separate the x's and the k's, we get that we want dp of x minus s sub x plus a sub k. Once again, this is constant with respect to x, and this is constant with respect to k. So we can once again pre-compute the best value for this over the previous layer, and then for a given k, just ask for the pre-computed value. And so we want the maximum of both, so that's it. That handles this transition. So that's it. Either we don't swap and we do this recurrence, or we do swap and we do this recurrence, and that's it. So we can frame both of these in terms of like child depends on parents or whatever, and then we can do these DP transitions. So in total, it's O of the number of nodes in this layer plus the number of nodes in this layer. And of course, the sum of nodes in all the layers is O of n, so this is like 2n or something. So the whole thing is O of n, which is cool. Because also finding maximums and stuff is O of n. So really that's it. If you want to visit my code, that's possible too. You could see how these transitions work within the code. I won't go too deep into it. Although what I do something different in terms of this. What I'm instead doing is for this transition, because I'm weird, I like did this differently. So it became like negative of sx minus dp of x plus a sub k. And then the pre-computed value would be the minimum possible value of this, and then it would all work out, but it's just slightly different. But yeah, that's how this works. So now we have f. How do we do? 34th. That is good. I like that. Yes, sir. Okay. Yeah, that's cool. So also good job, Gabe, getting 40th. Yeah. Right. So, and also second thread, and like everyone else, of course. It remains to go over f, so let's do that. Right. So you have an array. Keep holding my pen backwards. You have an array b1, b2, b3, b4, etc. I'm not sure if it makes sense to use values here, so we'll see. I may change that. And we're going to create some new array A. And, well, it must satisfy some conditions. Either AI equals BI directly, or the prefix sum of A. So either like, say we're fixing A4. Either these two are directly equal, or the prefix sum of the A values is equal to the B value. Note that this works because values can be negative and whatnot. So the prefix sum from j equals 1 to I of aj is equal to bi. You want to figure out the number of possible arrays A. That's how that works. Okay. Now, first, obviously, we know one array. We know that one array is going to be the just set AI equals bi for all I, right? So that gives us an answer of 1. And we want to figure out the number of other answers we get. So here's the idea. We're going to do some DP once again. And we're going to say that we have to modify this array at some point. So let DPI be the most recent place where we modified this array. So instead of AI equals BI, we made the prefix sums equal instead. And note that we forced that we have to explicitly modify it. If the value that would make the prefix sum the same and the initial values are the same, then it's not modified, so we can't count that. So DPI equals number of arrays where I is modified, I guess. And so the way this works is that we, so for example, say we're here. And then we don't care about the previous elements, we just care that this one was modified to make the prefix sum equal instead of the actual values equal. So now the question is, when are we allowed to do this? When will this not be equal to this? Or rather, we can sort of extract AI from this sum. So I equals 1 to, no, j equals 1 to I minus 1 of aj. And then we extract AI. So now we can set these two equal to each other and figure out when they're equal. So we set these two equal. AI is equal to AI plus the sum. I'm just going to use this notation. The sum from 1 to j minus 1. And of course we subtract this out, so we get that the sum from 1 to j minus 1 is equal to 0. This may be obvious for some people, but it is not for me, so I had to do this solving. But yeah, basically, we can modify this value and get something unique only when the prefix sum is not 0. So, cool. How's that work? And, well, the way it works is that we want this sum to be 0. So let's figure out transitions now. So if we're solving for like position 5, for example, note that say none of the other values are modified, then we automatically know the prefix sum. We know it's going to be the sum of these values. Otherwise, say some other value is modified. So for example, say this was the last modified value. So we're interested in dp of 2. I don't know why I'm using subscripts here, but just bear with me. So say dp2 is the last value that was modified, meaning all these values are unchanged, and we don't care about the rest of these. They're handled in this. So we know that b2 is the prefix sum, meaning that we know that b2 is the prefix sum, meaning that like all of the prefix sum of all of these values of a is going to be specifically equal to this. So the prefix sum we're interested in over the a values is going to be the dp value we inherit plus the values that aren't changed. So it's going to be b2 plus sum over b of 3 and 4. So if we're inheriting some value dp of j, then the prefix sum we're interested in is b sub j plus the sum from b of j plus 1, can't write it all, j plus 1 to I minus 1, excluding this. And we need this to not be 0. So if we let si be like the prefix sum over b's, like the sum from I equals 1 to, no, j equals 1 to I of bi, then this is equivalent to si minus 1 minus sj minus 1. And yeah, so that's basically it. We just need this value to not be 0, and then we can add this dpj to our current dpi that we're solving for, because we know that every value where the last value we modified is dpj is going to be valid. It's going to be valid in that this is different from the original array, because we know that the prefix sum is not 0. So really, dp of I is equal to the sum over j being less than I. Actually, the sum where j is less than I and si minus 1 is not equal to sj minus 1 of dpj. And then we gain an additional 1 if si minus 1 is not equal to 0. Because if this current prefix sum, where we have nothing modified, is not 0, then we can also modify this element straight away. And otherwise, if it is, then we can't. So, yeah. So another way to, so this is n squared, which doesn't work, but we can frame this in a better way. We can say instead that, let's just focus on this for now. This is going to be the sum just over j less than I of dpj, meaning it's the prefix sum of dp values, which is sort of another callback. But then minus the sum of j being less than I and si minus 1 is equal to sj minus 1 of dpj. So we take all of them and then just subtract out the ones where they're equal. Right? And then we can just like, this is something we can do easily. This is something we can use like a map for or something. We have count of x equals the sum of dpj where sj is equal to x, or sj minus 1 is equal to x. And then we just store this with a map. And then figuring out this value is just a running prefix sum that we have. And then this value is just a query to the map, where this is equal to count of s sub j minus 1. S sub j minus 1. A lot of suffixes here. A bit hard to follow probably, but yeah. So that's the idea. This is our transition right here. dpi is equal to 1 if this is true, if we can modify this element without having modified anything else in the past. And then the prefix sum over dp is minus the dp values where the prefixes are the same. Now in code, this turns out to be incredibly simple. Look at this. This is a div2f. We keep the count array. Now for each value, read it in. Say the initial value is the current value, which just turns out to be the answer, because the answer is 1 because we could have the initial array be something, and then it's just the sum over all I of dpi. So this ends up like being the running answer that we have. So it's the current answer minus the count of the current prefix sum. And then we again factor this in. If the current prefix sum is not 0, we add 1 to it, then add it to the answer, and then add it to the count array, and then add the current value of the prefix sum. And then we add 1 at the end, and that's it. This is a div2f. That's just amazing. And yet it's still hard. Like not the most amount of people solve this. How many people did solve this? Oh, well, someone FSD'd A. How would you FSD A? What happened there? I guess you can do a small enough value and have it not work. Wow, you would have like done really well though. That's unfortunate. But okay, right? So like, how many people saw this? And look at what the hell are these scores? This is crazy. Yeah, this is crazy. We have some people that solve like 4 problems in total and like a totally different set of them, because they're all like sort of similar in score if you solve F really late. So that's kind of interesting. And yeah, we see a similar thing. People solved F and this guy solved 3 to me. Yeah. Anyway, that's cool. That's all the solutions. Solved everything. Proud of that. And we'll do the edge around on Monday, and we'll do a stream on Sunday. You can check out the poll, see the beginning of the video for that, etc. That's all I have, so goodbye.